Hi class, this video is on topic C5, electric potential energy and electric potential due to point charges. Lately we've been talking a lot about charged parallel plates where there's a uniform field, but now we're going to go back to point charges. And recall that when we say point charges, we think of all the charge concentrated in the middle of the object, just as a way to simplify things. And most of our equations today are valid for what we call, for what we'd say point charges, or if we had a sphere with an evenly charged, like a surface that was evenly charged, like a Van de Graaff generator. So today we're going to look at electric potential energy and electric potential difference due to point charge. Sorry, not difference. Electric potential due to point charges. And so yeah, just that reminder that this is what we've done most recently. We talked about change in electrical potential energy or potential difference while moving a charge within a uniform field, such as the parallel plates setup. But now we're going to talk about point charges where the electric field strength depends on the location. So unlike in this case, anywhere inside the field, it was uniform, epsilon. We no longer have that. Okay, so one of the big learning goals of this unit was to understand how the different fields are similar and different. So let's just take a moment to recap and review. So we've got comparison of the forces of chapter 6 and chapter 7, Newton's universal law of gravitation versus Coulomb's law. And we had these new constants, these two different constants. When the field strength is known or constant, then we could use a different force equation, and they look similar as well. In gravitational force, we were talking about masses. Electric force, we were talking about charges. So comparing field strength, that the field that creates these forces, we can rearrange the force equations to get an equation for electric field strength or gravitational field strength. So gravitational field strength is the force per unit mass. Electric field strength is the force per unit charge. So that's why the mass and charge are kind of analogous. We also have these equations for field strength if you're talking about the individual, or sorry, the mass of the planet or the charge of the larger charge that's creating the field. Okay, having this comparison side by side, I hope you see some similarities. And you will have to, by assessments, you will have to pick and choose equations. So make sure that you've compared equations and know when they are applicable. So in C3, topic C3 video, we compared in these 3 rows, but then we also learned about gravitational potential energy in the last chapter. And so let's fill out this last row here. So gravitational potential energy and electric potential energy, they are both forms of potential energy, which means the energy is stored and it's available to turn into something else. So potential energy naturally wants to go down. So an object that we lift up to have gravitational potential energy, if we let go, naturally it will fall down. And if we have a positive or negative charge near each other, we could hold them apart and there's that stored electric potential energy. But if we let go, then they naturally want to come together, reducing the potential energy. So we can store the energy and then it could turn into another form. This should be EG and EE for our 2 forms of potential energy. So for gravitational potential energy, EG, it describes the energy stored when 2 objects with mass are held at a certain distance apart. So EG equals mgh. This is an equation we've known from before, but that constant G, it is we can sub in the field strength equation for it and see a more full gravitational potential energy equation that would be valid anywhere in the universe, as long as we would have the mass and the radius of the planet, or the center to center distance of the planet, and like the moon or the satellite. So just a reminder that we could only use that G equals 9.81 if we were talking about Earth and if it was close to Earth's surface. So there were some conditions that we used this last year, but now this is more applicable. But notice that EG, the equation for EG, there is a negative, and we know EG is always attractive. So, or sorry, the force of gravity is always attractive, and the EG has a negative, and there's no way for us to substitute in negatives here. These are all positive numbers, so that means EG is always negative. And so negative potential energy means attraction. So it's important to keep that in mind as we move forward. Electrical potential energy is EE, and it describes the energy that's stored when two objects with charge are held a certain distance apart. I'll let you read the cartoon. So for point charges, I have a question for you. So you already kind of know what's going to happen if we hold this positively charged object away from this negatively charged object. So maybe this is Raymond's sock and Raymond's sweater. When we let go, what will happen and why? And then what type of energy is increased as they get closer? Where is this energy coming from? So just take a moment to pause and think about the answers there. So for number one, they will move towards each other because of the law of electric charges. Opposites attract. So we knew that from grade 9. And how do they move closer to each other? There is an electric force, an attractive electric force associated with point charges that we learned this year in grade 12. And Newton's second law says that if there is an attractive force that's unbalanced, there will be acceleration. So specifically, these two, the charges will accelerate towards each other due to Coulomb's law. And the force creates the acceleration, according to Newton's second law. So what type of energy is increased? Well, as objects speed up, they increase kinetic energy. And where is this energy coming from? So this kinetic energy, we know from the law of conservation of energy, must come from somewhere. So this kinetic energy was formed from stored potential as we were initially holding them apart. So I think of someone holding these 2 point charges away from each other before we start watching what happens when we let go. And we have to put energy into holding them apart. And that was stored electric potential energy that was transformed into kinetic energy as they could crash in towards each other. Electric potential energy can be attractive, and then EE is negative, or repulsive, and EE should be positive. I guess I should say the force could be attractive. The FE force could be attractive or repulsive, and that means EE is negative or positive, depending on whether we have opposite charges or same charges. For a system with two charges, Q1 and Q2, separated by a distance r, the electric potential energy is, so this is an equation that looks really similar to gravitational potential energy. We have E here instead of G. We're using a different constant. We're using Coulomb's constant. So there are no new variables here. It's just a new mathematical relationship. So K is Coulomb's law, and we're going to be using 8.99 times 10 to the 9 newtons meters squared per coulomb squared. There are some really useful links that I'm going to refer you to, but sometimes they use 9 times 10 to the 9, and that's only one significant figure. I would accept answers based on that number, but you would have to remember to round your final answer to one significant figure, which is rounding a lot. So I prefer if you use 8.99. If you have anything multiple choice, it will be based on options using 8.99 times 10 to the 9. And then you have your Q charges, and R is the distance from the center of one charge to the center of the other. And how do we deal with the fact that it could be negative or positive based on whether it's repulsive or attractive? So the good news is that as long as you include the sign in the charge, we are going to be using the sign in the charge to get this. I said, well, how is it similar to EG? Instead of masses, we had charges. Instead of big G, we have small k. It was still r and not r squared. So note that the force equations had r squared, but the energy equations was only r. And then the big difference here, EG had a negative. So it was always attractive. But with EE, we know sometimes it's repulsive and sometimes it's attractive, so you have to put in those signs. And opposites attract, so positive times a positive gives you a positive. You have repulsion. Negative times negative gives you positive, also repulsion. And then if they're opposite, you get a negative and you get attraction. So let's try an example. Sphere A has a charge of minus 5 times 10 to the minus 6 coulombs, and sphere B has a charge of 2 times 10 to the minus 5 coulombs. Calculate the electric potential energy when they are 108 centimeters apart. So what do we have that's given? We always have small q, Coulomb's law, Coulomb's constant. We have both charges. It doesn't matter which one we put in which place. I always like to have the bigger charge first, just by like just out of habit. 108 centimeters, we got to convert it to SI units, and then we sub into our equation for electrical potential energy, remembering to put in the signs because that's what gives us a negative energy. Negative potential energy means attractive, and then we round to 2 significant figures. Part B says, how did the energy change as we dig, calculate the, I guess this is part A. What was the energy at half the distance? So kind of part B is saying, let's do it all over again, except our denominator is half. So we get an EE that is double, which makes sense mathematically. If our denominator goes up by 2, then the value of the fraction goes up, or down. Wait, sorry. If our radius, so if our denominator goes down by 2, so if it's halved, then this is doubled. The value of the fraction is doubled. So we get negative 1.7 joules once you crunch those numbers. And how did the energy change as we decreased this distance? So as you half the distance, you double the energy. Okay, so we've got a graph. Let's take a look at our axes. So it's EE, electrical potential energy, at different distances for 2-point charges. So first of all, notice that as they get farther and farther apart, so this is the distance between them, as they get farther and farther apart, it doesn't matter whether they are like charges or opposite charges, our energy approaches 0. So when you're infinitely far apart, there is no stored energy between them. The blue line is for if you have 2 like charges. Two like charges. And as they get closer and closer, the EE is big and positive. A very strong repulsion will push them apart. So there's a lot of stored energy, and if we let them go, they'd fly off. So the stored electrical potential might turn into kinetic energy. So this red line is for unlike charges. So we have a positive and a negative. And as they get closer and closer together, so smaller r, the electrical potential energy is very big and negative, indicating a strong attraction. And if they're allowed to be together, they will they will naturally want to be together. And there's a lot of energy that would have to be put into if we wanted to separate them, if we wanted to undo that, what they naturally want to come together. So there's a change in potential energy that we can calculate through this formula. So let's say we're moving the 2 point charges from Ri to Rf. This would be the equation that we use in order to calculate the difference in the energy from one point to the other point. Just every delta is a final minus initial, so that shouldn't come as a surprise. Electrical potential, or V, describes the amount of electrical potential energy present for 1 coulomb of charge at a specific location. So do you remember this? Do you remember this from past lessons? I say is equal to by definition. So V equals E over Q. And let's take that equation and combine it with our electric potential energy for point charges. And then if this gets subbed in there, do you see how the small q will cancel out and we'll be left with kq over r? We get this equation that reinforces what we've said before, that the only charge that matters is the charge that is creating the field, or a charge that creates the field. And the other object's charge, like the test charge, it's not there in the equation, which is good. So for potential difference, we also can call this voltage, which is, I find, way less confusing because electric potential energy and electric potential are just one word apart. So voltage is based on the location within that electric field. So it makes sense that the Q cancels out. And then we have electric potential due to a point charge that if we have multiple point charges, and we're not talking about a test charge, they have significant charges themselves, we can find the total electric potential at any point in or around this space. And we do that, we calculate the potential based on just Q1, just Q2, and just Q3 at that specific location, and then we add them all up. So for example, if we wanted to find out the voltage located at the center right here, so just to recap that the units of voltage are joules per coulomb. So it tells us if we put a 1 coulomb charge, that's how many joules of energy it would be possessed. But we don't have a charge, it's just telling us the joules per coulomb. So at the center here, we're not going to place something there, but if we were going to, what would be the effect of being near 3 point charges? So we would say, based on this distance and this charge, and K, what is the voltage because of 1, voltage because of 2, voltage because of 3, and then we would just add them up, or it's the algebraic sum. Sphere A has a charge of -5 × 10⁻⁶ coulombs. Calculate the electric potential, aka voltage, at a point 65 centimeters to the right. So this is a big negative charge. We tend to say like the positive charge is the test charge, but there doesn't actually have to be a charge here for us to be interested in the voltage at that point. So let's draw that example. So we've got Q and we've got R in SI units, so we converted centimeters to meters. This could have been microcoulombs. If it was 5 microcoulombs, then you do times 10⁻⁶ to get it into coulombs. So voltage is KQ over R. Notice it's not R squared because we were kind of used to, with Newton's universal gravitation equation and Coulomb's law, to do R squared. So we might be in the habit of doing R squared. Make sure you realize it's not. So we get -6.9 × 10⁴ volts. And you can think of the the sign, positive or negative of the voltage, just think of it like, because it's proportional to energy, just think of it like energy. So if negative, like whether it's attractive or repulsive. So in this case, we had a negative charge, we get a negative voltage, that would be a negative energy, so it would be attractive. Let's place a positive charge on the origin of this graph, and this charge is creating a potential that is KQ over R. And let's take a second positive charge. So that corresponds to the blue line, so it's positive. And let's place that some distance R away from this. So let's place it like here. And you know that there will be repulsion, and it will want to move towards the V equals 0 asymptote. So you know it will want to move to increase the radius. On the other hand, if your second charge was negative, so that's the red line, you'd know that there would be attraction. So R would get smaller, and you would be going into a larger and larger negative potential. Pay attention to the reference for electric potential. And for point charges, use the standard convention of choosing V equals 0 at an infinite distance from the source charge. In other problems, choose the Earth's surface as V equals 0 because the Earth conducts charge well. I've put this slide in here because there is a homework question about what happens to potential energy and potential when you have a proton versus an electron. So just come back to this slide and just remembering that what naturally happens for the positive charge, if this is a positive charge creating the field, it naturally has a decrease in potential or voltage. Naturally, the negative one has an increase in the potential. So it's getting a bigger and bigger negative potential. But in both of these cases, if you let go of the positive or the negative charge, that movement is motivated by decreasing the potential energy. Just like the ball that we lift up, the gravitational potential energy wants to decrease. So the ball, if we let go, the ball will come down and release that stored energy. So what happens when the charges move? So we've sort of already done this before. If we consider a positive point charge Q being moved from position A to position B within an electric field, we know these equations to be true. So we have a potential difference. So we did potential equals EE over Q, and now the change in potential, or the potential difference, is equal to the change in electrical energy over charge. And the same things apply as the, I think it was C4 topic, where we were talking about positive or negative work. So you have to think about the direction of the force and the direction of the displacement, and if they're in the same direction, then work is positive. If they're opposite, work is negative. You don't see a force in here, but Q could be positive or negative, and delta V could be positive or negative, because delta E could be positive or negative. So let's do an example. Oh yes, and remembering that when we defined electric potential difference, we said the amount of work required per unit charge to move a positive charge from one point to another in the presence of an electric field. So this is not an equation that is dependent on whether it's a uniform electric field or not. So that's why we can apply it to when we had the parallel plate problems, but we could also apply it to this point charge problem. Okay, so for example 3, we have an electric shock is delivered to a student from a, quote, friend. It transfers 15 joules of electrical energy through a potential difference of 500 volts. What is the quantity of charge transferred through this shocking experience? Okay, so well, we have charge and we have voltage. And actually, sorry, this is potential difference. We can still say voltage, but at the end of the day, it's Q equals delta EE over delta V. So we do our energy divided by our potential difference to get 0.030 coulombs. Okay. I've been seeing lots of news articles about, I guess, changes since there's been mandatory closure of non-essential businesses and industries to prevent the spread of COVID-19. And, there have been some good changes and some bad changes, but I noticed that our electrical energy consumption in Ontario was the lowest in 15 years. So I figured since this is related to electricity, this chapter, I would just throw that in there and let you know that I also noticed the sale of video games are the highest, some sort of record high. And also air quality has improved. So those are interesting things to me. So it's time for you to do some practice questions. Make sure you complete the exit ticket for this video and submit the practice questions in Google Classroom. Have a great day, stay safe, and stay well.